Hi everyone, this is the second deliverable of the Potland 7. These are the conditions with which the silo was designed.
To perform the calculation, we start with the dimension of the conical hopper. Initially, we analyze flow factor graph at 40 degrees, taking into account the 5W 22 degrees and the internal friction angle 33 degrees, obtaining that semi-included angle is 21 degrees and 1.43 being in the hopper flow factor. For the hopper opening, we use a theoretical flow from a shown equation specific for cement and established its straight line. In this way, when graphing in Excel, we obtain that critical point being 60,993 Newton per square meter. Similarly, knowing the semi-included angle, we calculate the H factor with the dimensionless. Finally, we replace the values in the equation, obtaining a value of 1.31 meters. When calculating the hopper height, we are assuming a diamond of 5 meters. We was again the same include that angle and the previous slide calculate with the data replacing, we obtaining a value of 4.8 meters. To calculate the height of the cylindrical part, we replace the values in the total volume equation solving for height. We also convert the 500 tons to volume units. This way of obtaining a value of 14.76 meters in height. Now to know the total height, we add the value of the hopper height and the cylindrical part giving a value of 19.57 meters. Moving on to the laws on the walls, these calculations were performed in more detail in Excel. However, here we took the horizontal person value necessary for the calculation being 36,840.52 Pascal. For the case of normal person in the hopper, 3 reference points were taken, upper, intermediate, and lower. The stresses were calculated taking the horizontal person value, the radius and thickness being the circumferential stress. For the meridional stress, we took the vertical person, the radius and thickness. Also for the shear stress, it was calculated using the radius and the thickness. All these stress are in megapascals units. For the thickness calculation, it was performed for both the cylindrical part and the hopper. They were calculated, however, more safe and adequate values were assuming. We also reviewed the von Mises yield criterion, which tells us that the yield must be less than or equal the allowable stress, managing to meet the criterion theoretical.
This is the technical plan of the silo from 2 points of view.
This is a front view, this is a top view, and this is a close view of the hopper.
The filling system is essential for transferring cement, which is a mix of clinker and additives. This material is highly abrasive, so the process must ensure a constant and uniform flow without segregation. The system not only moves the material, but also protects both the product and equipment. Therefore, hopper and silos must be built with wear-resistant plates, especially in impact zones where cement is discharged. A cable-activated personal protection system is also recommended. It should be made of cast aluminum to withstand abrasive conditions. For lifting the material to the silo, a bucket elevator with chains is required due to the weight and abrasive nature of cement. Dosing belts are installed in the hoppers of each component, clinker, gypsum, limestone, and pozzolan, to regulate the material flow into the final stage of the process. Finally, cement is usually combined pneumatically because it's a fine powder, although this method involves high cost.
As has been mentioned, cement is a powder and is a handling. Records rigorous safety control. The Plages dieback filter is one of the most efficient, having a high air-to-cloth ratio, allowing an amount of air equal to the locked area that must be controlled and prevent the environment from becoming dirty, for which that location system is adequate for this problem. Instrumentation is key for process control, process dosing, and structural safety. Height detectors or level sensors are used in the shear hopper and the silo to monitors. It is of great importance to monitor the person on the walls, since the high stress are located at the hopper cylinder intersection during emptying. Some risk prevention elements are temperature assured detector, thermometric probes, and explosive meters.
Discharge system. The hopper designs must ensure a uniform flow and avoid clogging. It should be step and smooth. A higher hopper reduces structural pressure but slow discharge. Bilge feeder control the flow. Guillotine valves regulate or stop the passage, and rotatory valves are installed under dust collectors. Access and maintenance. Safety focuses on preventing explosion and corrosion. Regular cleaning is required. avoiding flat surfaces where dust can accumulate. Floors must be smooth, machinery grounded, and static avoided. Electromagnets project against material parts, while lignite rods, extinguishers, and external control room increase safety. Filters are designed for easy maintenance even in tight spaces.
Flow conditions analysis. For Portland cement, mass flow is ideal. The graph validates a disk compare mass flow versus funnel flow. The upper line represents mass flow, where the material flows uninterrupted. The lower yellow line represents funnel flow, high probability of blowjacks and dead zones. Our cement, with a flow factor of 1.43, is located in the mass flow zone, mathematically confirming that with our 21-degree angle we will achieve reliable flow. If we had designed for funnel flow, we will be in the yellow zone with a guarantees obstructions. Furthermore, mass flow is absolutely necessary for three fundamental reasons. First, extreme cohesiveness of the cement. Second, for its hygroscopicity. And third, for the homogeneity of the product. Verification of designing criteria according to applicable standards. The Salary designing is based on a robust international regulatory framework, organized into five categories. First, the European EN standards governing structure design. For geometry and flow, we applied Eurocode 1991 to for NXC and Genkai theory, confirming that the 21-degree Hopper angle guarantees mass flow. This established how to calculate silo loads and size steel structures, complemented by ISO 11697 for bulk material loading methodology. Second, the American ASTM standards specialty, the silo material, especially A572 grade 50 and A588 steels. These define the properties of low alloy steels, ensuring a strength of 345 megapascals and durability against the corrosion. With wheels, according to AWS D121 third, the international ISO standards and established load calculation methodologies for the Colombian Technical Standards (NTC) 1950 and guarantees local compliance. And finally, OSHA and NFPA safety standards that protect personnel and prevent fires and dust explosions.